Hoover Dam was never poured as one giant wall. If it had been, reclamation engineers calculated that the concrete would need about 125 years to cool to ambient temperature. Thermal stress could have cracked the mass apart. That figure belongs only to the rejected single continuous pour scenario. It was never Hoover Dam actual cooling time. The real answer stood near the downstream cofferdam, an industrial refrigeration and pumping plant. It chilled water, then sent that water through steel pipes buried inside the rising dam. The system was temporary, and it cooled concrete during construction. It did not freeze the dam, circulate refrigerant through it, or keep the completed structure refrigerated. Why would fresh concrete need machinery that could make the equivalent of 1,000 tons of ice a day? Because concrete does not become stone by simply drying. Cement reacts with water in a process called hydration. That reaction binds the mixture and releases heat. In an ordinary slab, heat can escape through nearby surfaces. Hoover Dam was 660 feet thick at its base. Deep inside a mass that large, the heat had a long path out. The core could remain hot while the exposed concrete cooled sooner. Scale made the imbalance worse. As a placement grows, its volume increases faster than its exposed surface area. More reacting cement produces heat, but proportionally less surface remains to release it. A thin wall sheds heat. A dam-sized mass traps it. Then temperature becomes force. Cooling concrete contracts. If the exterior cools and shortens while the core remains hot and expanded, the two regions restrain each other. That restraint creates tensile stress, and concrete is far less forgiving in tension than in compression. A large enough temperature difference can open cracks. So the engineers needed more than cold water. They needed a construction sequence. Divide the dam into manageable masses. Let each mass harden. Remove its internal heat first with river water, then with refrigerated water. Allow the cooled concrete to contract. Finally, seal the planned joints so the separate pieces act as one structure. Reclamation began working on that sequence before Hoover's first concrete was placed. Researchers studied cement chemistry, aggregates, block dimensions, temperature, and grouting. They developed a lower heat cement for the main dam. But a better mixture could not make such an enormous volume lose heat fast enough by itself. The crucial field test happened at Owyhee Dam in Idaho in 1931. Engineers embedded pipe in a 4-foot concrete lift and circulated river water through it. Actual concrete surrounded the pipe. Actual water entered cool, absorbed heat, and returned warmer. The measured results showed that heat could be carried out from inside mass concrete at construction scale. The test section was not a tabletop sample. Reclamation's history describes a 28 by 210-foot placement. Engineers could compare calculated temperature behavior with measurements from a real lift, then carry a demonstrated method into Hoover's much larger construction plan. 2 years later, the idea moved into Black Canyon. Cableways stretched between towers above the site. They lowered bottom dump buckets into forms while crews spread each load with shovels and rubber-booted feet. Pneumatic vibrators worked air pockets out of the fresh concrete. But every bucket entered one part of a much larger pattern. Hoover Dam rose as about 215 separate vertical columns. Their faces carried interlocking keyways, so neighboring masses could eventually transfer load across the joints between them. The columns changed size with the dam. Near the upstream face, some were roughly 60 feet across. Near the downstream face, others were closer to 25 feet. Instead of one trapped body of heat, the builders had created hundreds of masses whose temperature and movement could be controlled. At this stage, the rising structure was not yet the single body visible today. The keyways shaped the column faces for a future bond, but the joints still had to remain available for cooling and contraction. The apparent fragmentation was temporary and deliberate. Each column climbed in lifts only 5 feet high. A block could receive no more than one lift in 72 hours, and the highest columns could not rise more than 35 feet above the lowest. The construction site therefore changed shape constantly. Buckets descended, crews worked one lift, and the dam advanced across the canyon as a field of giant steps. Before a new lift covered the last one, workers laid loops of 1-inch steel pipe across its surface. The next concrete placement buried those loops. Once hidden, the pipe became a heat exchanger inside the block. The first cooling stage used Colorado River water, or water-cooled against the surrounding air. It entered colder than the concrete and left warmer. Continuous circulation replaced the warmed water with a cooler supply, carrying hydration heat out instead of waiting for it to cross hundreds of feet of concrete. The water did not dry the concrete from within. It did not have to touch every grain. The steel pipe separated the circulating water from the concrete while heat crossed into the cooler flow. In effect, each buried loop brought an internal surface for heat removal to a place the canyon air could not reach. River water started the job, but it could not bring every block to the final temperature engineers required. That was why the refrigeration plant mattered. It chilled the second stage water to roughly 35 to 40 degrees Fahrenheit, about 2 to 4 degrees Celsius, and pumped it through the same embedded coils. This was the Title S refrigeration system, a temporary construction plant cooling water for buried pipe. More than 582 miles of 1-inch pipe spread through the structure. The plant's rated daily capacity was equivalent to making 1,000 tons of ice, but the project was not packing ice into the dam. It was moving heat out through controlled circuits. The network also let engineers control sequence. River water cooling could operate at one elevation while refrigerated water worked through a lower level. Temperatures were monitored, circuits were switched, and an 8-foot slot through the dam's center kept main pipe connections accessible while the work climbed upward. This meant the entire dam did not enter one cooling stage at once. One level could be hardening, another losing its first heat, and a lower section approaching its grouting temperature. The construction site contained several physical states at the same time, each tied to a different next action. As heat left, each block contracted. Narrow spaces opened along the joints that engineers had deliberately placed between columns. Those openings were not evidence that the dam had failed. They were the movement the construction plan had been designed to produce before the structure was locked together. Sealing too early would have trapped later contraction inside the finished dam. Instead, crews waited until a section reached its target temperature. Then they forced a thin cement and water grout into the opened keyed joints under pressure. Reclamation S-account places that pressure at about 300 pounds per s-ecant square inch. The grout penetrated the planned spaces and bonded neighboring columns. Cooling pipes that had finished their job were cut off and pressure grouted as well. As each section was sealed, the central access slot could be filled upward behind the completed work. The sequence reversed the most alarming visual sign. A narrow opening between concrete masses might look like damage in a finished dam. During construction, that same opening was evidence that contraction had occurred where engineers expected it, and while crews could still fill it deliberately. Only then did hundreds of controlled masses become one monolithic structure. The columns limited how much concrete generated and trapped heat at once. The pipes removed heat from their interiors. Refrigeration brought them to the required final temperature. Contraction opened the planned joints. Grouting closed those joints and completed the structural whole. Construction cooling finished in 1935 while work on the dam was still being completed. The embedded pipe remained buried, but the refrigeration stopped. Hoover Dam did not spend 125 years cooling, and it is not still being refrigerated today. The 125-year figure describes the construction path engineers refused to take. Their achievement was not finding a way to wait faster. It was separating one impossible problem into controlled stages of heat, movement, and time. The method also outlived the project. Embedded pipe cooling proved useful enough that Reclamation applied the same basic temperature control idea to later mass concrete dams. Hoover did not make every future dam identical, but it helped establish a practical engineering language for controlling concrete at enormous scale. the finished dam hides that sequence behind one continuous surface across Black Canyon. Inside are the remains of a temporary cooling network. Between the old columns are joints deliberately opened, filled, and made structural. Hoover Dam had to be refrigerated because concrete at that scale was not passive stone. It was a heat-producing material whose temperature determined how it changed shape. The dam could become one enduring mass only because its builders first treated it as hundreds of separate pieces, cooled each stage, and joined the whole.